So this video is all about exercises on finding and describing the row space and the column space of a matrix M. And the first note here is that we can actually use the row operations to reduce M, because by row operations we can make more zeros, and sometimes we get a zero rows, which definitely help us to find the correct dimension of the row and the column space, and also to describe those spaces. And for example, if you look at such a matrix M, and for example, after the reduction, you are arriving at something like that, something like that. So because not all the matrices are of square size, right? Let's say M now has a size which is not square, so we don't exactly have a diagonal. So that's why the upper triangular matrix doesn't exist. But what I'm saying is that you have to try your best to make the lower left side to have as many zeros as possible. For example, if you're arriving at a reduced matrix form like this, I think it's quite clear that if you look at the row space, I can just pick all the four vectors to be in the basis of the row space, right? Because it's quite clear that all the four vectors are of different directions first. And for example, like the second row cannot be generated by the last two rows, right? Because the last two rows don't have non-zeros at this spot. And similarly, the row 1 cannot be generated by the last three rows, because the row 1 has a non-zero spot on the first spot. But no matter what linear combinations you do on the last three rows, you are not able to get a non-zero on the first spot, right? So it gives us a sense that if you're able to do the row operations to reduce the matrix to this form, it definitely helps us to find the basis and the dimension of the row space. And let's start this exercise now. So please look at the current matrix M. It is 3 by 3, and I would like you to find the row and the column spaces for the matrix M. And please also give me a basis of such a space. And now, first of all, let's do some row operations. For example, we can reduce the second row by using row 2 minus 2 times row 1. We can also reduce the last row by using row 3 plus row 1, right? And the row 1 remains unchanged. The row 2 would be something like this. And how about the last row? It's gonna be something like this. And I think it's quite clear that we can reduce it further. For example, I can use row 3 minus 2 times row 2 to reduce the last row, right? So at the end, you're getting a new matrix like this, and it is upper triangular matrix. And we can look at the row space. Row space, and please recall the fact that the row space is not the same as the column space. For the row space, it's not changed by the row operations. It means that we can directly look at the M prime to determine our row space. So basically, it is spanned by some row vectors, and you see, now we basically on all the three rows, we have the non-zeros along the diagonals, right? So I think it's quite clear that we can simply use the first row, the second row, and the last row to be the basis of the span of the space. So this basically form the basis, because the basis now has three vectors. It means basically it's a three-dimensional space, and in R3, basically it means the span of these vectors is basically the whole space R3, right? And let's look at the column space now. So you see, because of the fact that row operations actually change the column space, if you are insisting on using these three columns in a new matrix to form the column space, and it's not a good idea. Most of the time you will get it wrong. And it's much better to look at the original matrix when you look at the basis of column space. And if you look at it this way, and obviously these three vectors they are of different directions, and for example, like the last column cannot be generated by the first two columns, right? Because the first two columns has zero in the last spot. And no matter what linear combination you use for the first two columns, you're not able to get the last vector anyway. So it gives you a sense that all the three vectors point to a new dimension for the vector space. Basically, it means the column space of M prime is going to be just the span of the three vectors, and these three vectors essentially form the basis. Because they are of different directions, no vector can be written as a linear combination of the remaining vectors. And in that case, it means basically for M prime, the column space is basically the three-dimensional space in R3. It essentially means the whole space R3, right? And for the original column space M, we have to do the same thing. And because we know that all the column vectors are of different directions for m prime, all the vectors give new dimension. Basically, it means that I can use the original 3 columns to span the column space of M. Basically, I will do the column space as the span of the 3 vector like this. And we automatically understand that it must be a 3-dimensional space. And basically, it means it must be R3, basically. So that's the answer to the column space and the row space. Let me write it here as a conclusion. So basically, for this 3 by 3 matrix, the answer is pretty obvious in the sense that for both the row space and the column space, they are just basically the whole space, R3. And let's look at another example now. So please look at the current matrix 3 by 3 case, and let's do the row operation first. So you can notice that in the current case, you can get the second and the last row completely zero after the row operations. And if you try to look at the row space, basically it's spanned by the 3 rows because the fact is that row operation never change the row space, and also the last 2 rows are completely zero. It basically means the row space is only spanned by the first vector, which is the only non-zero row, right? And row operation never change the row space of M, so it means I can simply use the reduced form. It means we have the row space as a span of only one single vector. So if you try to describe such a row space in a qualitative way, this one is basically a one-dimensional space in R3. In R3, because now the vector has 3 coordinates, right? And one-dimensional space means it's basically a straight line. The direction of this straight line is determined by the direction of the row vector here. And let's look at the column space now. For the column space, we have to be slightly more careful. We cannot simply use the column vector on the new matrix to form our column space. For example, if you look at the M prime here, the 3 columns are like this, and it's obvious that all the 3 vectors point to the same direction, right? I think it's obvious because you see C2 prime is minus C1 prime, and also C3 prime is basically 2 times C1 prime, right? So all the vectors point to the same direction. And it basically means if you look at the basis of the column space, we don't have to use all the 3 vectors. We just have to pick one of them because they give the same line anyway. So let me write it down here. The column space for the M prime, I can simply use the span of just the first vector, and basically that's it. But as I told you already, for the column space, the operation changed the column space. So we have to go back to the original matrix. And this kind of relation still satisfy for our current matrix M among the column vectors. So we can simply use this fact because we can simply choose the first column to be the basis vector for the column space. Same thing, I can simply choose the first column of the original matrix M to be the basis vector of this column space. And because our basis only contains one vector, it essentially means once again, we can describe the column space as one-dimensional space in R3, and it is basically a straight line when we call it one-dimensional. And the straight line is determined by the direction of this vector. And that's the end of this example. And let's look at one more. So please look at the current matrix now, and let's do some row operation first. So that's the reduced form of the matrix, and of course, we can also swap the 2 rows. The reason to swap the 2 rows is we try to maintain the shape of the new matrix to be something like upper triangular matrix like this, even if it is not a square matrix. Anyway, please look at the non-zero spot for the 3 rows, and let's look at the row space. Once again, for row space, it doesn't matter much. We can use the updated matrix to directly write down the basis, because we actually have 3 non-zero spots like this in the upper triangular matrix. It basically means if we look at the basis of the row space, we can just pick the 3 vectors, which is the first row, the second row, and the last row. So what does it mean? Please look at each vector. Now each vector has 5 coordinates. It means the row space is sitting in R5, right? So basically it's a 3-dimensional subspace inside R5, and we use the basis like this here to describe the row space of M. And let's look at the meaning of the column space. So you see for the column space, we have to be slightly more careful. First, if you simply focus on the last matrix M prime here, after all these row reductions, Of course, we can pick three vectors to be the basis of the column space here. Based on the non-zeros, I can pick the first one, the third one, and the fourth one. So what does it mean? If you call the three column vectors to be C1 prime up to C4 prime, it means the column space of M prime is gonna be spanned by basis elements, which are C1 prime, C3 prime, and C4 prime. And by using this fact, we can go back to the original matrix. So it basically means our column space of the original matrix is basically spanned by a basis which contains three column vectors. And based on these three, basically C1, C3, and C4. And if you look at the original matrix, C1 is here, C3 is here, C4 is here. Basically, I can use the basis as C1, C3, and C4 like this. And let's try to describe this column space. See, each column vector has three coordinates, right? It means anyway, the column space must be sitting in R3 because each vector has three coordinates. And because we understand that our basis now has three columns as the basis vectors, it means it must be a three-dimensional space in R3 because the dimension of our column space is the same as the whole space. It simply means our column space is basically R3, right? Basically the whole space here. And that's the end of this video.